Okay, so this video is going to be a short intro on thermodynamics in terms of chemistry. All right, so let's just kind of get into it. All right, so big here, we're just really talking about energy. When we're talking about thermodynamics, we're talking about how energy are flowing, how energy flows through a chemical system. Okay, so first thing, what is energy? And when we're talking about energy, it's just the ability to do work or to produce heat. All right. And there's basically two different types. You have potential energy, which is just energy of position, and then you have kinetic energy, which is just the energy of motion. All right. And so, which leads us to temperature. All right. Now, temperature, I think there is a huge misconception on what temperature is. Most people think about temperature as, how hot something is or the amount of heat something contains, but that's not necessarily true. When we're talking about temperature, we're talking about the measure of random motions of the components, all right? So the faster the components are moving, the higher the temperature. All right, and so I'm trying to, hopefully I'm illustrating this here. So if you have hot water, if you notice in this image that the water is moving faster. And so the faster it's moving, the higher the temperature. The slower it's moving, all right, the lower the temperature. All right, and so water doesn't move as quickly, its temperature is not as high, it's not as energetic. Okay, so that's all temperature. So the higher the temperature, the more energy those molecules or substances have. Okay, the slower the motion, the lower the temperature. Okay, and so when it comes to that, then we could talk about heat. Now, heat is the flow of energy between two objects where there's a difference in temperature, when there's a difference in its movement, all right? And so kinetic energy gets transferred from one substance to the next. And it's always, the kinetic energy always flows from, or heat always flows from hot object to colder object. Always what has more energy to what has least amount of energy. And so like here in the instance, here for example, we have hot water, all right, in a container with a thin barrier next to cold water. Well, because of that, we will see that um, energy could be transferred from what's hot to cold. All right. And so eventually, what's going to happen, what's hotter will tend to lose energy to what's colder. The colder will gain energy. And then at the very end of the day, you'll notice that they're both will have the same temperature. They're both, the molecules will be moving with the same amount of kinetic energy, or they will contain the same amount of kinetic energy. All right. And so that's just kind of the big thing on that one. Um, so once again, flow of energy always going from hot to cold, always going from more energy to least amount of energy. All right. And so this is the reason why if you touch something that has more energy than you, it feels hot. All right. And so it has more kinetic energy, and the transfer of energy is entering to you. So that's the hot feeling versus something that has lower kinetic energy than you, or it's colder than you. Anytime you touch it, it feels cold. So energy is leaving from you to it. All right. So like example I gave is like you have the stove right here, right? And so you're touching the stove, or at least the electric stove, and it's hot, it's running. Um, it feels hot to you because it has more energy. Versus if you touch snow, all right, snow has lower energy than you, kinetic energy, and so when you touch it, energy, heat is being transferred from you to it. Okay. Now, when it comes to thermochemistry, there's usually terms that we like to do just to help us to categorize substances and help us to figure out how energy is flowing back and forth. All right, and so just important vocabulary terms that you just need to know: system and surroundings. System is basically anything that we're talking about, anything of focus, any object of focus. All right, and surroundings is just anything that's around the the system. So, like for example, if you look at this picture here, you will have, or you could consider that the cup is your system, all right? And then anything that touches the cup, like the hands here, or anything around the cup, is your surroundings, okay? And so that's all that simply means. All right, and so There's two basic processes how energy could be transferred in and out of chemical reactions. So, or any physical chemical reactions. We have exothermic and endothermic. And the name itself should kind of give you an idea what's going on. Exo meaning exiting, thermic meaning heat or energy. So anything that's exothermic, energy is leaving the system, all right, to the surroundings. So energy is leaving, is flowing out of the system and is entering the surroundings. So exothermic, exiting, heat exiting the system. While you have endothermic or inter, so energy, thermic, enter, endo, energy flows into the system from the surroundings. All right. So it's either energy is being expelled or energy is being absorbed. All right. Now, sometimes we'll graph it. So here's a graphical representation of an endothermic process. So in this case, it could be an endothermic chemical reaction. All right. And so just a couple of things that you need to take to watch. So here, your x-axis in this case is time. All right. So over a period of time. Your y-axis is joules, so the amount of energy. So joules is basically the unit of energy. All right. Now, if you notice here that the reactants of the chemical reaction will have this much energy. So at this point of y, that's how much energy it will have. Now, over the process of the chemical reaction, when it becomes products, it has this much energy. All right. And now, if you compare the two, you notice that the products actually have more energy than the reactants. All right. And so this lets you know that all in all, that this is an endothermic process. All right. Why is it endothermic? Because the reaction needed energy in order for the product to take place. All right. And so the product has more potential energy or has more energy within the bonds or within the or whatever it may be. But there's more energy in the products than you have of the reactants. So this is an endothermic process. All right. While for exothermic process, it's the exact opposite. So once again, you have in your y-axis, you have energy, which is in joules. All right. Um, Here, sometimes they say the reaction coordinate. That's just how the particles are coordinated with one another. But at the end of the day, you can even look at this as time as well. But all in all, the way you interpret the graph is still the same way. So if you notice, here are your reactants, and it has this much energy. Here are your products, and it has this much energy. So if you notice, there's a decrease of amount of energy as this reaction has taken place. And what's in the center here? We'll talk about this next unit, this in a couple of minutes. But if you notice, there's a difference in energy. All right. And because there's a difference in energy and energy dropped, all right, so we'll call this process an exothermic, all right, because the reactants lost energy in order to make the products. All right, so this is an exothermic process here. So just make sure that you're able to interpret these graphs, what we call energy profile graphs. Okay. Um, and so let's just look at a couple examples of physical endothermic, exothermic processes. Okay, so here's an example. So from the point of view of the ice, so if the ice was your system, right? So I'm just going to kind of write that down. Your ice is your system. Okay, you're holding it with your hand, your hand. All right, so your hand is your surroundings, right? Is the system experiencing an exothermic or endothermic process? All right. So here, yes, it's experiencing an endothermic process, but if you think about it, right, which one has more energy, the ice or your hand? All right. Your hand has more energy. So because your hand has more energy, remember, heat always travels from what's hot to cold. So heat will be traveling into the ice. And so because it's traveling into the ice, it makes the ice is experiencing an endothermic process because it's gathering, it's taking in energy from your hand. And this is the reason why it starts melting in your hands because it's taking in that energy. Okay, let's look at another example. So, from the point of view of a hot cup, so your hot cup obviously is going to be your system, okay? Um, and you're holding it with your hand. So, again, your hand, and so this is your surroundings, all right. So when you think about it in terms of the system, it's an endothermic, exothermic. Well, you have a hot cup of coffee. You touch it with your hand. What's hotter, your hand or the cup? Well, you feel the heat, so that means the cup in itself or the coffee is hotter. So energy is leaving the cup. So if energy is leaving the cup, and the reason why it feels hot because you're feeling that energy, all right, the energy that's coming from the cup itself. So that makes the system experiencing the exothermic process. And if the system is experiencing an exothermic process, well, then that means the surroundings, all right, is experiencing an endothermic process. All right, so it's always kind of backwards. The system is getting the exo, the surroundings are getting endothermic. Okay. All right, so let's get another example here. So you're putting a cup of water in the freezer, all right? So the cup of water in this case is your system, all right? The freezer is your surroundings, all right? And so if you put the cup of water into the freezer, you have to think about which one is warmer, all right? And whatever is warmer is always losing energy. Well, the cup of water will be warmer. And because the cup of water will be warmer, is going to lose the energy to the surrounding because freezers, when it's plugged in and working, it's typically colder. All right, so this is the reason why this is an exothermic process. And if you look thinking about that, the system, um, is the cup of water. Okay. Here's just, I think this is our last example. So we're boiling water on the stove. All right. So you take water from the faucet, I put it in the pot, you place it on the stove. All right. You turn on the stove. Water is now beginning to boil. All right. So the water in this case is your system. All right. The stove in this case, which is on, is your surroundings. All right, so here's your stove here. This is the water that we're talking about. So which one's hotter? Which one is releasing the energy? Which one is taking in the energy? Hopefully you realize the stove is giving energy to the water. And so anytime you're boiling something, every time you're melting something, you gotta give it energy in order to melt and to boil. So in this case, this is an endothermic process. Okay. Um, And so let's just look at a couple examples here. So, or two examples. So those what we just talked about earlier before are physical examples. So boiling, melting, um, just touching something that's hot, touching something that's cold. These are all physical processes of endothermic, exothermic. You also could look at it from a chemical process. So if a chemical reaction takes place, here's an example. So when we boil water, heat energy changes liquid water into steam or water vapor. This is an example of an endothermic process, endothermic physical process. Okay. Um, and well, let me just draw this arrow so that you can see what I'm talking about. So in order to turn it into steam, you need energy. All right, so when propane gas is burned, combined with oxygen, carbon dioxide water is produced. Heat energy is released. This is an exothermic chemical reaction. So you had propane plus oxygen produces carbon dioxide, water, and some energy. And so because it produced energy, or energy is a product, all right, it is considered to be an exothermic chemical reaction. All right. Um, so that's a big thing there. If it was like for example, photosynthesis, photosynthesis, and I'm just going to kind of write this on the side here, It's basically CO2, so carbon dioxide plus water, and it needs energy from the sun, creates sugar plus oxygen. All right, and so because it needs the energy, or energy is a reactant to input, this right here is considered to be endothermic. All right, so depending on what side energy is on, depends on if it's an exothermic or endothermic process. All right, so just kind of moving on to the next point. All right, so when it comes to chemical reactions, all chemicals typically have some sort of some amount of energy within it. All right. And that energy, we call it enthalpy. All right. So when we talk about the enthalpy of a substance, we're talking about how much energy is within that substance. Okay. We cannot measure the actual energy that's within the substance at all. But what we can measure is what we call the enthalpy change, or the delta enthalpy. Okay, and so enthalpy is usually given to us as a capital H. All right, so when you see a capital H in chemistry, that's enthalpy. And when we're talking about the change of enthalpy or delta enthalpy, it's just this triangle H. Okay. Now, when we look at it from a using a energy profile graph like this, like I'm showing you here, all right. And so if you have an exothermic process, all right, the change of enthalpy, the change of enthalpy is going to be negative because it lost energy. Remember, enthalpy is just how much energy a substance has. And so if it loses energy, then it lost enthalpy. So delta H, all right, will be negative, is a negative number, all right? If it's an endothermic process, so that means over a period, over the chemical reaction, it increased the energy, all right? So there's the enthalpy has increased. That means the amount of energy it contains, it increases, all right? So delta H, all right, will be positive. All right. So anytime you see a negative delta H, it's an exothermic process. If you see a positive delta H, it's going to be it's going to be an endothermic process. All right. Now, let's just kind of talk about the units that delta H is in. All right. So delta H for chemical reactions, its units are typically given to us as kJ per mole. All right. So kilojoules per mole of that substance. Okay. And just once again, if the reaction is exothermic, it's negative. If the reaction is endothermic, it's positive. All right. So that's just a big kick there. All right, so let's just kind of go through how we go about answering or determining um, enthalpy changes of a chemical reaction. Okay, so here's a chemical reaction here. I'm going to write in black. Okay, so it says that Sa plus AO2 yields 8SO2. All right, I kind of don't like the way it looks like here. When it converts itself to this program, it just looks funny. So I'm just going to rewrite it here. Whoa. Okay. So S8 plus 8O2 yields 8SO2. All right. And it tells you that the delta H of this reaction is negative 2,368 kilojoules per mole. Okay. So what does that mean? So that means when S8 plus O2 reacts to create SO2, all right, overall, it loses negative 2,368 kilojoules per mole. So one thing that you could definitely figure out, you could tell already, because this is a negative number, this process is an exothermic process. All right. So it lost energy. It had to release energy. Okay. Now, the question asks, how much heat is involved when 25 moles of sulfur is burned in excess oxygen? Okay. So, how do we figure this out? Okay, so we're trying to figure out how much heat. All right, heat is always in joules alone. Okay, I gave you the enthalpy. Okay, so the enthalpy here, if you pay attention, is delta H is equal to negative 2,368 kilojoules per mole. All right, so you try to figure out how much energy, so simply in joules alone, all right, or some form of joules. In this case, because enthalpy is in kilojoules, it's fine. We could probably figure out the answer in kilojoules. It's perfectly fine. All right, when 25 moles of sulfur is burned. Well, if you look at the enthalpy, right, it is basically for, in sulfur's case, it is negative 2,368 kilojoules of energy for every 1 mole of sulfur, S8. All right, because when you say per mole, that's really just 1 mole. And then when we look at the chemical reaction here, it says that for every 1 mole plus 8 moles of O2, you get 8 moles of SO2. All right, so for every 1 mole of S8, this is how much energy that you create. All right, so now if we want to know how many by 25 moles, then we could just simply use dimensional analysis. So negative 2,368 kilojoules per 1 mole of S8. Well, how many moles of S8 are we talking about in this problem? 25 moles. Okay, so if we're talking about 25 moles of S8, we could simply cross this out, math purposes, and then this will get us, if you put this in a calculator, 59,200 kilojoules. All right. Oh wait, I'm sorry. Negative 59,200 kilojoules. Okay. And so that's how much energy will be produced if you were to burn 25 moles of this. Okay. I think it's simple enough. But let's just go through more examples. Second example, same equation. All right, so what if how much heat was involved if you had 275 grams of sulfur that's burned with excess oxygen? All right, so once again, enthalpy, all right, is always kilojoules per mole. Okay, this time I gave you the question in grams. So the first thing you need to do is you need to convert 275 grams of sulfur to however many moles of sulfur. All right, and so what you will see here is that you need to figure out what is the molar mass of sulfur. All right, now here sulfur is S8, so there's 8 sulfurs combined together. All right, and so the molar mass of sulfur is 32.065, right? And simply because there's 8 of them, you have to multiply this by 8, and you'll get about 256.52 grams per mole. So that's your molar mass of S8. Okay, so let's convert this to grams or to moles. So 275 grams of sulfur, all right, multiply that. So we know for every 1 mole of sulfur, or S8, is equal to 256.52 grams of S8. Okay, so when you plug this into the calculator, which I'm doing right now, 0.52, you have 1.072 moles of S8. Okay, so now that's how we know how many moles of S8 we have. So then we could go back and figure out how much energy is being created with this many moles of S8. So we have 2,000 or negative 2,368 kilojoules for every 1 mole of S8. All right, and then so if you multiply this by this number here, so every 1.072 moles of S8, we cancel that out, it will give us, and you put this into the calculator, you should get your total negative 2,538 let's say 6 kilojoules. All right, so that's how much energy is being released. All right, so let's look at another question. So it says how much heat is involved when 150 grams of sulfur dioxide is produced? All right, so once again, remember, as I said, this right here is in moles. And so when you think about it, for in this case, for this question, all right, and so it is, you'll create 2,368 kilojoules of energy for every 1 mole of sulfur dioxide you create. All right, and so we have to really pay attention to the stoichiometry, or the coefficients of your balanced chemical equation. But first thing first, they gave it to you in grams. You're gonna have to convert this in moles. And I'm usually a big fan of just doing everything in one smooth problem. All right, so here we have 150.0 grams of SO2. The very first thing I want to do is convert this into moles of SO2. So you plug into your calculator the molar mass of SO2, where you have one sulfur and two oxygens. So I get a molar mass that's roughly 64.1 grams of SO2. This cancel this out. So now I know that when I do this calculation, it's going to be in moles, which is great. All right. Now when I pay attention to this, oh, I just realized I said something wrong, but I'll fix it now. But all right, so when you look at the energy here, you have negative 2,368 kilojoules. All right, that's how much energy is created. But how many moles, all right, that's created this, all right? And I apologize, I said 1 mole here, but really when you look at the chemical equation, it's when you create 8 moles. So the amount of energy that is released in this case is because you have 8 moles of SO2. All right, and then you have to show that when you're writing, trying to figure out how much energy of sulfur dioxide is being created. So for this much energy to be created, when you create 8,000 or 8 moles of SO2. All right, and so this way you could cross out your moles of SO2, and then all you have to do is just type in what you have here on the calculator, and you'll get, so the answer you'll get is negative 692.7 kilojoules. All right, and so that's how much energy is produced when you have 150 grams of sulfur dioxide that's produced as well. Okay. So that's how this question works. And I think there's one more example. All right, so the question asks here, how much energy is produced when 85 grams of sulfur reacts according to the reaction below? All right, so let's look at this reaction here, and I'm just going to rewrite it because I think it's going to just be easier to see. So you have 2S plus 3O2 yields 2SO3. And then once again, it's always going to be important that these reactions, chemical equations, are balanced, because the coefficients will definitely tell you what's going on. And the delta enthalpy for this overall reaction, the delta H of this reaction, is negative 792 kilojoules per mole. All right. Now, we're trying to figure out how much heat is produced when you have 85 grams of sulfur that reacts. Okay. So we're starting with 85 grams of sulfur. All right, and once again, since it's in grams, the first thing you want to do is convert this to moles. All right, and so if you use the periodic table, we know that for every 1 mole of sulfur, it's 32.06 grams of sulfur. So this cancels out. All right, now now that this is in moles, then we could just figure out how much energy is produced, all right, based off of the mole ratio of the equation. So we know that overall you'll create negative 792 kilojoules, but how many moles of sulfur are we talking about? Well, let's just look at the chemical equation here. In chemical equation here, we have 2 moles of sulfur. So that's what I'm going to put down here. All right, it's whatever that coefficient is. And so that will cancel out your moles. And so all you're left with is kilojoules, that's exactly what we want. And then all you have to do now is plug this into the calculator. And so when you plug this into the calculator, you should get, so negative 1049.9 kilojoules. And so that's how much energy is produced in this chemical reaction. All right, so that's thermodynamics.